Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber-Physical Systems, IISc. Today's talk is by Professor Krishna Jagannathan, and he will be speaking on quantum Q channels as building blocks for quantum communication networks. Professor Krishna Jagannathan obtained his BTech in Electrical Engineering from IIT Madras in 2004 and the SM and PhD degrees in Electrical Engineering and Computer Science from the Massachusetts Institute of Technology in 2006 and 2010 respectively. During 2010 to 2011, he was a visiting postdoctoral scholar in computing and mathematical science at Caltech and an off-campus postdoctoral fellow at MIT. Since November 2011, he has been with the Department of Electrical Engineering, IIT Madras, where he is currently an associate professor. His research interests lie in the stochastic modeling and analysis of communication networks, network control, and queuing theory. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Professor Jagannathan directly. Over to you, Professor.
Thank you very much for the kind introduction. I'm very honored to give this talk at CNI. Thank you, Parimal and the organizers for inviting me to give this talk. I hope my audio was clear and I hope that my screen share is working out all right. Yeah?
Yes, all fine.
Okay. If you have a question, I prefer audio cues. So please do stop me if something is not clear and if you have a question. Sometimes I may not see the chat because I'm seeing the full screen. Okay. So please feel free to interrupt me whenever you have a question. This talk is about quantum Q channels as building blocks for quantum communication networks. All right. This is a collaborative work with my colleague Abhishek Chatterjee in my department and Prabha from physics. And towards the end, when I speak about some networks, I have included some recent work of my PhD student, Jaswanti. All of us are at IIT Madras. Okay. So what is this talk about? So this talk lies at the intersection of quantum information theory and queuing. Okay, you can view this as marrying these two fields, quantum information theory and queuing. So we derive fundamental limits of classical communication using quantum states that decohere as they traverse through a network of queues, right? So at a high level overview of this talk, we have a basic building block of quantum networks. We define something known as a quantum Q channel, okay? We will tell you a lot more. Most of this talk is about this quantum Q channel and its capacity characterization. Is there a question? Something in the chat? I don't think so. Okay. All right. So this is about the basic building block of this work is a quantum Q channel. A quantum Q channel models sequential processing of qubits at a node. Okay. In particular, it models waiting time dependent noise or waiting time dependent decoherence of quantum states. Okay. Our contributions include considering a quantum erasure Q channel, which is the simplest kind of a quantum noise models or quantum erasures. We consider a quantum erasure Q channel and derive the exact capacity of a quantum erasure Q channel as a function of the stationary waiting time in the queue. We also have an upper bound for additive noise. I'll tell you what additive noise is in a little bit. It's a somewhat technical condition. Let me show what is it. Yeah. So additive noise channels or additive Q channels, we have a classical capacity upper bound for the channels. Okay, that's a fairly general upper bound of capacity. Then we put together these quantum Q channels. So each quantum Q channel can be thought of as a node. Okay, where qubits wait to be processed or served. Okay, and we put together these quantum Q channels to build a network. In the case that if these Qs are Markovian Qs, this kind of network is called a Jackson network. For this network of Markovian Q channels, we are able to obtain exact capacity expressions. Okay, so this is the broad outline of my talk. So this is about again, it's the marriage between quantum information and queuing. So the basic building block is a quantum Q channel, which models sequential processing of qubits and waiting time dependent decoherence. We derive capacity expressions for such Q channels, and finally put these Q channels together and talk about quantum Jackson networks. All right. So that's the overview of my talk. Yeah, we derive capacity of quantum Jackson networks, optimal pumping rates, optimal routing probabilities. All this can be derived once you put these Q channels together. Okay. So a pictorial snapshot. Here is a Q. This arrival rate is lambda. You have lambda bits per second of arrival and mu bits per second of service. So this is processing mu bits per second. What is the highest rate at which information can be sent through this queue? The answer is, of course, that it can be arbitrarily close to mu bits per second. You can obtain any mu minus delta, right, at the expense of delay, right? You can get as close to mu as you want at the expense of delay, correct? So that's for classical bits. We want to answer the same question for qubits, quantum bits, okay? Instead of classical bits, suppose this ρ1, ρ2, ρj are quantum bits. They are density operators. Just think of these rows as ρj's as 2 by 2 matrices which have unit trace and non-negative matrices with unit trace. Although that's not all that important for the purposes of this talk. So these are qubits. The thing with qubits is that when they propagate through optical fibers, or if they are held in an optical buffer, they tend to decohere. All right. So that is where I'm getting at. Now here, this guy processes mu qubits per second. What is the maximum rate at which classical information can be sent through this queue? This is qualitative. This seems like a very fundamental question that we should answer, right? And that's what this talk is about. Okay. What we will show is that it's strictly smaller than mu. Okay, you cannot get arbitrarily close to mu, and that's because of this concept, this issue of decoherence. If you just leave classical bits in a disk, or you want to transmit them, they may suffer noise, but they don't. The states don't die, so to speak, whereas quantum states just decohere, all right, after some amount of time, and that's where the quantum communication is different. Okay, it's fundamentally different. And this decoherence is an unavoidable, inevitable physical phenomenon. Okay. Is that okay? All right. Qubits decohere as they wait. All right. So this is the key issue of this talk. When you buffer qubits, quantum states in an optical fiber loop, or if they, there are propagation delays when you send these qubits over long distances, they always interact with the environment and suffer a waiting time dependent noise, okay, which some people call decoherence. All right. So the longer they are waiting, or the longer they propagate, longer they interact with the environment, the more likely that they lose information, that these quantum states lose information. Okay. So for some specific numbers here, if you have superconducting qubits, their average coherence time is about 30 to 100 microseconds. All right, so this is roughly the amount of time a superconducting Josephson junction state is alive. All right, whereas the time to make gate operations on such a qubit is about 300 nanoseconds. So there's roughly a factor of 300 between these two, right? And similarly for there are other technologies. So the bottom line is that the processing time is only about the coherence time, the amount of time that these quantum states are alive is only about 2 orders of magnitude more than the time it takes to process any one of these qubits. All right, and this is a phenomenon that we don't see in classical communication. All right. So we model the sequential processing of qubits at a node using something known as a quantum Q channel. Okay, that's what I'll speak about next. Now, I'm going to be mainly talking about erasures. Okay, erasures in the quantum world are pretty much exactly like erasures in classical communication.
Krishna, I have a question. Can I ask the question now?
Yes, yes, yes.
Yeah, can you go back to the previous slide? I couldn't understand the meaning of processing time and the sort of the analogy of processing time in the classical queue versus the quantum queue.
So these two, it's okay. These may not be very state of the art, and I think I took them from Scientific American website. So this is typical gate times. So if you're running a gate operation on a quantum bit, this is the amount of time it takes for that gate operation, right? So you're looking at a quantum in a gate and a bunch of quantum bits coming at a gate, right? So it takes this long to make the gate operation. Okay.
No, but what's the analogy with the classical queue which you showed a couple of slides back? Where is the gate? You showed a service time there.
Correct, correct. Yeah, yeah. So this is
Service time?
yeah. So this is mu 1 by mu.
So this is mu. Okay, fine.
Okay, so this is 1 by mu. Okay, and all I'm saying is that the amount of time that these quantum states are alive is only about 2 orders of magnitude higher than the processing time. Okay, depending on the technology of implementation, it could be better, and these numbers are getting better. I mean, they do live for longer, but this issue is very much a real issue. Okay. Okay, so here is so I'll speak mostly about erasures. I'll briefly mention other noises. So what's a quantum erasure? You take a quantum state rho j, it remains unchanged. Okay, it remains as rho j with probability some 1 minus p. Okay, now this, why have I written 1 minus p of wj? I'm going to model this as a q. All right, so I'm getting a little ahead of myself in notation. I'll tell you what this is. Okay, and rho j is mapped to a fixed erasure state E with probability p. Okay, so P is the probability of erasure, but I'm going to call this probability of W. This probability of erasure is P of Wj. Okay, I'm going to model this as a function of the waiting time in a queue. All right. So I'm going to say that, you know, the longer it waits, the more likely it is to decohere. So if I wait, if a qubit is waiting for a longer time in a queue, the more likely that it's going to get erased. Okay. So this is an example of exponential decoherence. So that the coherence times are exponentially distributed with some parameter kappa, but it doesn't have to be exponentially distributed. It could be any increasing function of the waiting time is good. Okay. So erasure probability is time dependent. By time dependent, I mean waiting time dependent. Rho j is the jth qubit, let us say, which waits for wj amount of time. The probability of erasure is modeled as an explicit function of that waiting time wj, p of wj. Okay, and the constant kappa. This, if you are looking at this kind of exponential decoherence, this constant kappa is inverse time constant. It depends on the technology of implementation, whether you are using NV centers or superconducting qubits, and other physical parameters such as temperature. Okay, so let me tell you a little more about what a quantum Q channel is. I told you that the erasures are waiting time dependent, but I should tell you a little more about the queue itself. So you have a single server queue with quantum states arriving at rate lambda and getting served at rate mu. All right. So rho j is the jth qubit sent to this queue. You have a classical bit stream. Okay, a source generate classical bit stream which are encoded into qubits. Okay, and sent to this queue. They're sequentially sent to this. This is continuous time single server queue, and the arrival rate is lambda. This guy can process mu bits per second. Okay, we assume that the processing time of each qubit is also a random variable. It has some generic distribution fs and some mean mu. Okay, and we can take mu equal to 1 for ease of notation. Okay. So this mu is roughly 1 by 300 nanoseconds. Okay. In the previous context of the previous question. Wj is the waiting time, the total time spent. Okay, I'm going to talk about it as waiting time spent, waiting time of the jth qubit. So dj is the departure time, aj is the arrival time of that particular qubit. So dj minus aj is the total time spent in this queue. All right, that's wj, and I'm going to model the probability of erasure of any of these qubits as an explicit function of this waiting time wj. Okay. So the erasure Q channel, the probability of erasure of the jth qubit is modeled as an explicit function P of Wj. Okay, so that goes back to what I said in the previous slide. And this P of Wj is could be some generic increasing function. It could be any increasing function. We will specifically focus a bit on exponential decoherence with some parameter kappa. Okay. Are there any questions on the model? No questions?
So
Okay.
just one question.
Uh-huh.
Is the erasure probability 0 when the waiting time is 0?
Yeah. Well, I mean the way I model 1 minus e power minus kappa w gives you that answer, right? If you have 0 weighting, you have perfect. The states are always preserved. The longer they wait, the more likely that it will decohere. Parimal, you have a question?
Yes, yeah. So Krishna, so it's clear that if you wait longer, your erasure will happen. But can you do some smart coding in time that? I'm just thinking out loud. Maybe it's not what you're going to talk about. So that.
Yeah. So
if I send more information later, that will not decohere because it's
yeah.
Not
so what you're talking about, I guess. Okay. So there's one aspect is coding, right? Can you repeat these states or something like that? That's a separate question.
Right.
That's a question that we are looking at presently, but for that we need to understand what happens without coding, right? If you just if you don't repeat or anything.
Right,
like
right.
that.
I was just thinking ahead in sense.
Yeah. It's a perfectly valid question, and we are looking at what happens if you have a repetition code or something like that going into this queue. You have some redundancy, but you're also increasing the load on this queue.
True. And second thing, also, I was thinking that what if you, like you do this redundancy across servers also, right? This information when you send, but I don't know like how this quantum information, how you mix it, and these things are not clear to me. So
Yeah.
Classical bits, I sort of understand. So can you throw some light on that?
So you're talking about something like a network coding.
Yeah, I mean, not necessarily. Well, so so you can send. So one thing is again redundancy, right? You send the same information to say multiple queues, right? And so you wait less, maybe because you're now splitting your stream into multiple servers, right? And you would see that it'll decohere less because you're waiting less, right? So multiple servers should give you some advantage if you have parallel servers, right?
Yeah, if you have parallel servers, you can analyze all that, right? But before that, you have to analyze this.
Right. But also you could do something clever that, which is classical information bit can be coded, right? That so sufficient number of them finish, then you will say that I have received the information. But in quantum information, I'm not sure how these mixings will happen.
Yeah. So even if you just forget the fact that these are quantum bits, let's say they're classical bits that decohere, right? Forget how you do it in the quantum world.
Right.
I think these are non-trivial even with classical objects, right? But my submission is that if you don't understand a single node and waiting time dependent noise, I think we cannot go ahead. And if you understand this, I think we can build a lot on this. Right. And that is what we are trying to do.
No, the motivation is clear. Thanks. Yes.
Thank you. And also, I think you made another valid point about, I'm assuming some kind of a stationary point process arrivals, right? So it's as though these photons carrying this information are arriving according to some Poisson process or something. But in reality, maybe you can control this flux, right? You can send it such that the weighting is lesser or something like that. So those also lead to very interesting control problems. Right. So you see that the moment you put this down, you have like an explosion of problems you can consider. Right. But my submission is that you have to take this very simple, understand the very simple mg or mmq or whatever, and then go ahead into doing parallel queues or coding or optimal pumping or whatever. Any other comments? Thank you.
Yes, I have one question. So,
yes,
sorry, train of thought. I'll come back in a little while. Okay.
Sure.
As you were talking, my train of thought got lost. I'll come back.
Okay, sure.
Yeah. Okay. I remember now. Okay. My question is this: when a qubit decoheres, you are saying it gets noisy, but I guess your model is you just lose it, right?
Yeah. So this is there are many noise models for. Just like there are many noises in the classical world, there are many, perhaps even more noise models in the quantum world. For the purposes of this talk, we are focusing mainly on erasures. I will briefly mention what happens if you have more complicated noises. All right. So our model is that rho j is either preserved perfectly or is erased altogether, from which you retrieve no information. Okay. So I think that's the easiest model to consider, because just like in the classical world, the quantum erasure channel is one of the easiest models to consider.
So effectively, the model is that when the waiting time of a qubit, I think we can forget about qubits, when the waiting time of the entity reaches W, for a given waiting time, with the probability of rho W is lost. That's all.
Yeah, correct. So you can think of, so the P is a function of the waiting time. So P of W is the probability that having waited for W amount of time, the bit is lost.
Yes. Okay.
Thank you. It's like a CDF. It's a CDF of waiting time, coherence times. Okay. In fact, what I plotted in that earlier figure, this is a exponential coherence times. This is just a CDF of an exponential with parameter kappa. Okay. Although this form is widely used, our work doesn't require this. Okay. Any other questions? I hope this model is clear.
One query regarding the model. Again, coming from the conventional noise systems, should the bit not be susceptible while it's being processed? Like, should the erasure probability not be a function of response time rather than waiting time?
Yeah. So this is we are actually taking response time. So what queuing theorists call sojourn time, right? Departure minus arrival. So this Wj is the instant of departure minus instant of arrival. So which is the total time spent in the system. So waiting time, I guess queuing theorists say waiting time does not include the time spent at the server, but we are including that. So maybe, I mean, as a queuing person myself, maybe maybe I should not be saying waiting time for this. I should be saying sojourn time, right? But I will be saying waiting time. But please understand it as the total system time, total response time. Okay. All right. So this is the erasure Q channel. Okay. Now, from a quantum information theory perspective, this is a non-stationary quantum channel with memory. Okay, so let me. So this is why the problem is somewhat mathematically non-trivial. So let me tell you what. So it's a quantum channel with memory. That's because remember the probability of erasure of a jth qubit depends on its waiting time. Which again is correlated with the Wj is correlated with Wj minus 1 and so on because of the queuing dynamics. So the probability of erasure of consecutive qubits are in fact correlated. I hope that is clear, right? So this is not a memoryless channel, right? This is a channel with memory. Also, it is non-stationary. It's a non-stationary channel in the information theoretic sense. Okay. What I mean is that you will send an n-long. Let's say you have n-long code word, n-long classical bit stream or whatever, and you're coding them into qubits and sending them. This n uses of this Q channel does not drive the Q into a stationarity. So you are sending n finite number of code words. So you have a non-stationary channel. Okay. So this is why the problem is non-trivial. It's a non-stationary quantum channel with memory. Okay. Is that clear? Any questions on that? These WJs, WJ minus 1, etc. are correlated. So the probability of erasure are also correlated. So the noise seen by consecutive qubits are not independent, they are correlated. Okay. Okay. So I'll go straight to the result. We have a capacity result for this non-stationary quantum channel, this quantum erasure channel, erasure Q channel. It's a single letter capacity for the erasure Q channel. Theorem, the capacity of the erasure Q channel is given by lambda expectation 1 minus P of W bits per second. Okay, so the answer is very nice and intuitive. After all, 1 minus P is the probability, is the capacity of an erasure channel per channel use. And this 1 minus P, P itself is a P of W. And this expectation is over the stationary distribution. Okay, so this pi here is the stationary distribution of waiting time W in the Q. Okay, so expected 1 minus PW you would expect is the capacity per channel use, and since you are making lambda channel uses per second, you get lambda expectation of 1 minus PW as the capacity of this Q channel. Okay, a few remarks are in order. This formula, the result does not depend on any specific queuing model or the functional form of P. So let me explain what that means. The functional form of P could be anything. It doesn't have to be that 1 minus e power minus kappa W or whatever. If P is continuous function of W, this is sufficient. Results do not depend on the specific Q model. I am not assuming any MM or MG or any such thing. What is required for the result to work is that this Q have a stationary distribution W. Okay, so this the waiting time should converge in distribution to some pi. Okay, and the expectation is over the stationary distribution. So there should be a stationary waiting time distribution, number one, and Q should satisfy ergodicity. So time averages should converge to ensemble averages. These are the only requirements. So for any ergodic stationary Q channel, you have this capacity theorem. Okay, and this is an information theoretic capacity result. So you have to prove a forward theorem and a converse theorem. The forward theorem is the achievability is fairly straightforward. It uses IID uniform distribution, fully classical strategy. You just have IID half, fully classical code, and you encode them into orthogonal quantum states, and you can show that this is achievable. Okay, you can use this Hans information density method to show achievability if you want. Information spectrum method, which some of you may be familiar with. So achievability is relatively straightforward, at least conceptually. You just have to calculate the information density. The converse is more involved because you have to take into account even entangled encodings and so on. Right? This is a quantum Q channel. This is not just a classical channel. So you have to take into account the possibility that these quantum states are themselves entangled and so on. The converse is more involved. It uses additivity of Holevo information for the erasure, quantum erasure channel. This Holevo information, for people like us, I think we can just think about the Holevo information as the quantum generalization of the Shannon mutual information. Shannon mutual information is a difference of two Shannon entropies, whereas the Holevo information is a difference of two von Neumann entropies. And this Holevo information is additive for certain channels, and erasure channel is one of them. We use that technical result to obtain a converse. Okay, this is where more the technical effort is involved. I don't want to get. I didn't want to introduce too many quantum information notation and theory here. If you are interested in this, I urge you to see this paper, and I will be happy to share a copy or answer any questions. If you can send me an email, I'll be happy to respond. Okay. So but this is the answer. All right. Lambda expectation 1 minus PW. So we have the capacity obtained. So we can do a number of things with it. Okay, so we can talk about, we are engineers. Many people here are engineers, presumably. So we can talk about how do I optimize this? How do I, how does it specialize for MG1 queues? Blah blah blah. Then we can talk about how do I put them together in a network and so on. All right. Okay, so let's do some calculations for the engineering design analysis sort of.
Krishna, just one question.
Yes.
To go back to the previous slide. Achievability, you said uses IID strategy. That's for the times at which the packets are the qubits are sent, or
there is no. Let me clarify. There is no timing channel involved here. The arrival process is just some stationary process. Think of it as a Poisson process. It is just the encodings are in the qubits.
Okay, got it. Yeah, we have no control over the.
Yeah. So this is not at all Anantram Vardu. It's totally different from Anantram Vardu. All the information is in the symbols. There is no information in the timing. Okay, so that's another direction we can go. I mean, if you can combine signaling in the timing information, that's another, it's another thing we can consider. But we are not considering that. This is just encoding in the symbols, and a classical code with IID half will achieve this. We can just calculate using the information spectrum.
Thank you. So another question, Krishna.
Yes.
You can ask the same question in the classical queue as well.
Yeah.
Where when a queue is when a bit is delayed, it is lost with some probability.
Yeah.
Depending on the delay, and there the answer will depend on the discipline. Whether you first come first serve. So is that same thing true here as well? The order of service of the qubits?
No. So actually, we started by doing this. We just had no quantum, and we just said these are classical bits which will die after some time. This was our paper in NCC 2019. To answer your question, this answer does not depend even on the service discipline. Okay, what will depend on the service discipline is the distribution of the waiting time. Right, so this expected 1 minus PW will depend on the waiting time, but this answer itself doesn't depend on the waiting time. In the service discipline. Yeah,
because I am sort of recalling some results from a very long time back in telecom, which had to do with impatient customers. And customers, if they were asked to wait for too long, if they were waiting for too long, they would simply drop out and go.
Right.
It's the same thing. And
it's the same thing.
That last come first served is better than first come first served.
So we have tried those calculations as well. It depends on in an MG1 queue. If you're fixing an MG1 queue, you can talk about for exponential decoherence times, is FCFS better or LCFS better, or all those calculations can be made. In fact, I'm getting a little bit ahead of myself. I'll show you how it depends on the service times, on the service discipline. So if you look at an MG1 erasure queue channel, we take, let's say, exponential decoherence times. We have C of lambda is lambda times expectation of 1 minus P of W, where P of W is that. So you have lambda times expectation of E power minus kappa W. This expectation of E power minus kappa W is the, what is it? It's the Laplace transform, right? It's the Laplace transform of the waiting time in the MG1 queue, evaluated at the decoherence constant, kappa, right? Which is the inverse time constant of decoherence. That's what it's saying. This depends on the service discipline. I guess that's what you're getting at, right? So if you have, I think this, you have the polar check engine formula. This depends on whether it's FCFS or not. Right, this is PK formula for an MG1 queue. This is the moment generating function or Laplace transform evaluated at kappa. Right. So this answer does not depend on the service discipline. This answer does. Okay. So you can calculate this. So here it's this is a standard formula, by the way, available in any queuing textbook like Plain Rock or whatever. So 1 minus lambda kappa by kappa minus lambda times 1 minus fs tilde of kappa. 1 minus fs tilde of kappa is the Laplace transform of the service time distribution. Remember, fs is the CDF, fs tilde is the Laplace transform. Okay, so you have a closed form answer. Okay, the capacity of the MG1 erasure channel is given by this expression. This expression is exactly the same as this expression. I have just made alpha as 1 minus fs tilde kappa over kappa. And for an MM1Q channel, this alpha is very simple. It's 1 over kappa plus 1. Okay, so you have very nice closed forms for this MG1Q channels. Okay.
Sorry, Krishna, one more question.
Yes, please go ahead.
So do you think part of the reason you're getting these results is because your impatience is in some sense memoryless, no? The probability of dropping off has exponential. If you change it, maybe results change a little bit.
The previous slide, the expectation of 1 minus PW, it does not depend on the exponential decoherence. Here we are assuming exponential decoherence, and I'm getting expectation of e power minus kappa W, which is the Laplace transform of the waiting time. Correct. So the answer to your question is that this expression depends on your assumption of exponential decoherence. And this is known. Bottom line is that the Laplace transform is known for MG1 FCFS. I should be saying MG1 FCFS erasure function. Right?
Thanks, Krishna.
Yeah, thanks. Okay, so that's the answer. I think the next I have a plot of the capacity against lambda. In fact, this plot, I mean, you can do all of this in the classical as well, except when you have quantum, you have to, the upper bound is much harder. Okay, that's it's a technical difficulty, but the intuition is all the same. You could just, if you have trouble visualizing quantum bits as what on earth they are, I think just think of these as bits that die, or, as Professor Anurag Kumar mentioned, you can just think of them as customers that just vanish. Okay. Erasures like a vanishing, right? They get served, but they're not useful anymore. So this is a plot of capacity against lambda for various coherence constants. Remember mu equal to 1. So kappa equal to 1 is the decoherence at the same scale as service, which is a bit unrealistic. You want the quantum bits to live longer. So maybe kappa equal to 0.01 is this curve, kappa equal to 0.1 is this curve. This is a plot of capacity against lambda. So you have, in all these curves, you have the capacity increasing versus lambda because you're sending more, right? So it increases first, it reaches a sweet spot and then goes down, right? And the qualitative behavior is because you're using more and more channel, making more and more channel uses per second. So it's increasing, but then the waiting time is also increasing. So Q is building up. So more and more erasures, lots of erasures, and only erasures, right? And so when lambda is very close to mu, you have an enormous queuing delay and all your data is junk, okay? So then you have nothing getting out at lambda very close to 1 mu. You have no useful information coming out. So there is some sweet spot lambda star, right? It appears from this graph, which you can actually find out analytically. What arrival rate is the Q channel capacity maximized? You have to argmax this guy, which happens to be a nice concave function. So you can calculate there exists a unique arrival rate lambda star at which the Q channel capacity is maximized, where this optimal arrival rate is 1 over 1 plus root of 1 minus alpha. Remember when this alpha is 1 minus fs tilde of kappa over kappa, right? Which is fs tilde is the Laplace transform. So this alpha is a function of kappa. Okay, so that goes back to this.
Can I ask one question, Krishna?
Yes, please.
So in this plot, if we take kappa to be very close to 0, then essentially you're back in the classical world where there's no erasure, right?
Correct. Kappa equal to 0 is 45-degree line.
Right.
Okay.
And would that be the capacity for the classical? Would that
lambda, right? It's lambda bits per second because you're sending lambda bits and they're all getting out correctly. Right. It's lambda bits per second. Okay. Point is, some of them are decohering here, so you're not going to get lambda, you're going to get something less than lambda, right? So it's lambda times 1 minus lambda by all that, it's a little bit less than lambda. And as it happens, there is a sweet spot phenomenon, which we have explicitly characterized here. And the sweet spot, so at what rate should you pump your photons, your qubits, to get the maximum information rate out, right? So if you have qubits which are superconductive Josephson junctions, which live 100 times longer than your gate times, so you're on this curve, so you should pump at 0.9 mu, and you will get a capacity of 0.81. Right, so that is what this is a fundamental result. You cannot beat this. Okay,
right. Thank you.
This is because you're losing some capacity. In this case, 0.81. So 19% of the server capacity, information capacity, is wasted because of decoherence.
Right.
Clear? Any other questions? You can also ask after, you have the answer, so you can do other things. What is the optimal service time distribution? So in the previous slide, we are optimizing lambda. Suppose you have fixed lambda.
Sorry. Question. So if you didn't code at all, then what would be, what is the coding gain? So you have the sweet spot, let's say you operate at that, but somehow you must code across in the qubit world, across the bits to be able to arrive at this, so that whatever erasures are there, you're able to make up for some of them. So if you did not code at all, if you treated each bit by itself, and then if you lost it, you just lost it. What is the number of uncoded transmission that you can get? I just want to know the gain from coding.
I don't know the answer to that question. I think at this point, what we know is that from the point of view, from a random coding perspective, classical IID half code is enough. So if you send IID 0-1 probability half, its capacity achieving. So if your code book, like 2 to the NR code words or whatever, is made with IID half bits, its capacity achieving. Okay. Is that clear?
I'll think about it. Yeah, please go ahead.
Yeah. So there are other issues that you could repeat symbols to improve their redundancy, but you will also increase the load, right? You think about, let's say you're repeating each symbol twice, right? And you will decode correctly even if one of them is not erased, right? So that gives you some redundancy, but you're also increasing the load now. Lambda becomes 2 lambda, right? So those issues I have not considered in this, right?
But you are coding across the bits. So if you look at the formula lambda times expected value with respect to the stationary distribution of 1 minus PW, that appears to indicate that even though IID 1/2 does not appear to indicate that there is coding, to achieve it, you might actually have to do coding. Correct. But when you look at that formula by itself, it seems that you can pump at lambda, and each one will suffer the stationary distribution, and which means no coding might give you the capacity. So I was just wondering whether that is indeed.
I think, yeah, that is my understanding presently. What you just said, I think, is my present understanding.
Okay, yeah, thanks.
I think you're right. Okay. We can also ask after the optimal service time distribution. So in this case, you fix a arrival rate lambda. So earlier you were optimizing this. So you fix a lambda, you fix a mu, but you are asked after what is the capacity maximizing distribution in an MG1Q channel. So arrival rate is fixed, average service rate is fixed. What is the G, the service time distribution that maximizes capacity? Theorem, the MD1Q channel, the erasure Q channel has maximum capacity. So among all G distributions, D has the highest capacity. Proof is just Jensen's inequality. So that's your capacity formula. Lambda is fixed, kappa is fixed. So you want Fs tilde of kappa, which you want it to be as small as possible to maximize capacity. But by Jensen's inequality, it's lower bounded by e power minus kappa expectation of S. So deterministic service times or optimal. In other words, if your processor should be deterministic, it should not have any variance, right? So these kind of engineering calculations can give you, can be done once you have the answer.
Hello, Krishna, I think the result is only for FCFS, right?
Correct. Professor, this whole formula is only for FCFS.
Yeah, right.
This expectation, this is PK formula of the Laplace transform of waiting time in an MG1Q FCFS, right? But, this answer is valid, but this equality assumes FCFS.
Right, okay.
Okay. Of course, actually for LCFS, we can, this expression is known, it's not this. We found out that if you're doing LCFS, MD1 is the worst, which is sort of weird. I don't know. It comes out from this. Okay, but for FCFS, MD1 is the worst, is the best. And you can do these calculations because the answer is no. Okay. So these are, fun calculations to do. Okay, so here is some more, quantum generalizations. I spoke only about erasures, where the erasure probability is a function of W. Generally, quantum channel is denoted as a map. Okay, it's a, it's a positive map, a trace preserving map, denoted by N. That map of the noise suffered by the jth qubit, we are going to parameterize it by the waiting time Wj. So it's some NWj that maps rho j to some other quantum state, which is the output. Okay, so NWj, you can think of it as taking rho j as input and spitting out some output quantum state. There is a notion of additive Q channels, which has, as far as I know, I don't think there's an equivalent of this in the classical world at all, but I'll roughly tell you intuitively what it means. Additive Q channel means that the Holevo information of the underlying single channel, use channel is additive. So what it means is that if you have two channels, so NW1, NW2, the tensor products channel chi, which is the Holevo information, is sums out into the sum of the Holevo informations of these two channels. I have not even told you what this chi is. Okay, I've just said that this chi is something like the mutual information, but more complicated. I've deliberately done that because I didn't want to get too much into the notation and theory of this. Intuitively, what does this mean? Additive quantum channels are those channels for which entanglement at the encoder, at the input will not help. Okay. So generally, a quantum channel, if you use entangled inputs, that is input that lives in a higher space, right? You can gain capacity. So generally, this Holevo information is super additive. But there are additive Q channels, are those channels for which this entanglement at the input does not help. You can actually code qubit by qubit transmission is optimal. So what we have is that for additive Q channels, we have an upper bound. Here is a theorem. For additive Q channels, the classical capacity is upper bounded by lambda expectation of pi, chi of NW. Okay, so chi of NW for erasure channels is 1 minus PW. Okay, and for other noises, it could be something else. And this upper bound holds for additive Q channels. Okay, if the underlying channel model is not additive, we don't know. Okay, but this is true for additive Q channels. Erasure is additive, and there are many other physically relevant channels which are shown to be additive. But for erasure, we have achievability also. We don't have achievability for a generic additive Q channels. We have in recent work, we have shown achievability for some specific channel models, including symmetric amplitude damping channel and broad class of channels known as unital channels. Unital channels are channels for which the state I by 2, the maximally mixed state, is always preserved. So if you send I by 2 into this N operator, you get I by 2 with probability 1. So for those channels, we have shown, of course, they're all additive, so this theorem holds, but we have also shown achievability. Okay. So at a high level, we have cleaned up the Q channel question for unital channels, symmetric amplitude, damping channels, erasure channels, a bunch of channels, a depolarizing channel and so on. Okay, but we don't have a very general answer. We have a general upper bound for additive Q channels and achievability for some relevant channels. Okay, so we started with Q channels, consider erasures. We have generalized to a bunch of other noises. The next direction of generalization is to put these Q channels together into networks, right? What I will speak about for the next 5 minutes is quantum Jackson networks with erasures. This is very recent work. We're using Q channels as building blocks. We can construct a network of Q channels to model erasures due to waiting times. So a Jackson network, Jackson network terminology is familiar to queuing people. It's a product form network where each node is like an MM1 queue. All right, it has exponential service, and you have Bernoulli routing between the nodes. All right, so you have exponential server here, and with probability Aij, you go from node I to node J, and that's what a Jackson network is. Now so that's 1970 stuff, right? I mean, this has been studied for a long time. What we are going to do now is to make each node not just an MM1 queue, but a Q channel, a Markovian Q channel. And then we are able to calculate capacity for some simple networks. All right. So just to go from simple to more complex, if you consider parallel Q channel capacity, you can just do similar calculations. If you have parallel Q channels with mu1, mu2, lambda splitting, Bernoulli splitting, blah, 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 you can get capacity results like so, just like using same machinery. And if you have exponential coherence times, you can calculate in terms of lambda, delta, and kappa. And you can optimize this capacity for, in terms of optimal pumping rates, fixed lambda, what is the optimal splitting, fixed splitting, what is the optimal lambda, all that you can do, just like we did it for the single Q. Okay. So this is a parallel Q channel. You can also look at a tandem Q channel in which bit stream goes. This is like a bunch of repeaters. Okay, you can look at it as quantum repeaters. Each node you wait for some time, so you may get erased, and then you go to the next one. Get erased, blah blah blah. Right. For this, the classical capacity of the tandem Q channel is given by lambda expectation of P sum of the waiting times. So here we are just modeling the probability of erasures as the probability is as a function of the total time spent in the system. So the sum of Wi comes up inside the P. One nice thing about these, if you have MM1 queues, by Burke's theorem, we know that these Ws are independent. If for a given qubit, the waiting time at time spent on each node is independent. So the sum of these waiting times, the Laplace transform, if you have P of W's 1 minus e power minus kappa W, the Laplace transforms will just multiply. So that's very happy. We can get this is just a product of all the Laplace transforms e power minus kappa W for an MM1Q. So you can get explicit formula. So this is a plot of capacity versus lambda for two tandem Qs, homogeneous mu1 equal to mu2. You get similar curves, except now you don't have concavity. Visibly, you don't have concavity. But there is a sweet spot, which you can numerically find out. Okay. So this is for tandem Qs. Now you can generalize. If you have a quantum Jackson network with Bernoulli routing, like so, Aij is our probability of routing from I to J. The classical capacity from a particular source to the destination in bits per second, when the coherence times are exponentially distributed, is given by this big mess. Again, in a Jackson network, the waiting time, the time spent by a particular packet or a qubit across nodes, they are independent, right? That's just Jackson network theory. And so you can multiply the e power minus kappa W terms and get this big expression. Here the psi I is the fixed point. This is the standard fixed point stuff of Jackson networks. Psi I is the arrival rate, is the composite arrival rate, including exogenous and endogenous arrivals at a particular node, right? And you can calculate these rates. And for simple topologies, you may be able to optimize what is the optimal routing probability matrix, what is the optimal pumping rates, and so on. Okay. Okay, so I think I'm running out of time. So let me summarize. In this talk, we talked about quantum Q channels. They are a viable model to capture time-dependent erasures when these quantum bits interact with the environment, when they buffer. This is a good model. We have not explicitly included propagation delay in our models, but I think our framework allows for it. You will get more complicated expressions. We have only taken queuing buffering delay into account. We have derived the capacity, exact capacity for erasure Q channel. We have a capacity upper bound for additive Q channels. Then we considered a network of Markovian queues, which is just a Jackson network, and that's amenable to exact analysis. More broadly, we think that this work highlights the importance of quantitatively understanding the impact of delay-induced errors or delay-induced decoherence in quantum communication networks. Thank you. Bye.
Thank you, Professor Jagannathan, for an informative talk. Are there any other questions?
So Krishna, one question not really connected closely with the subject, but can you tell a little bit about what entanglement means and signifies?
Yeah, so it's it's operating at a higher dimension. It's so instead of this qubits live in 2 dimensions. There are 2 by 2 density operators. If you entangled 2 qubits, you will get some 4 by 4 density operator, and generally it will be 2 power n. Okay, they are operators in 2 power n dimensions. Okay, so that's mathematically as much as we need to understand that they are density operators in higher dimensional space. Okay,
but any more intuitive?
Physically, see, it has some. I don't understand. I mean, you have to talk to an optics person or photonics person who do this. Yeah, I mean, you have experimentally. I really don't have any intuition on this. But there may be people in this very audience who know this stuff. Okay. Apparently, you use a beam splitter or something, and you get entangled photons. And I am as ignorant as you are in this.
All right. Thank
you.
We
can just think of them as big matrices. That's all.
Krishna, if we interpret the final answer, though, it says entanglement, at least from my interpretation, that you don't need to do any entanglement. It doesn't help in terms of the capacity. Because the lambda times the erasure, or 1 minus the erasure is the capacity.
Let me look. Yeah, for erasure, it doesn't help. That's correct. For this, so for erasure, you're right, it doesn't help. And additive channels are those channels for which entanglement does not increase capacity. And for that, this upper bound holds. Okay. There may be crazy channels which are not additive. Apparently, I mean, what I'm told is that so far, all the qubit channels that are known are in fact additive. Okay. But there is no theorem that says, there's a conjecture that says all qubit channels are additive, but it's not proven. Okay. Apparently, there are non-additive qubit channels, okay, higher dimensional channels. So that is just FYI. So if all qubit channels are additive, if that conjecture is true, this is true for all qubit Q channels, right? Achievability we have for certain, this is what I meant. So for certain unital models, symmetric amplitude damping and all, we have achievability. Okay. Erasure, you're right. Erasure is known to be additive, no use in entangling and all
When you started out the channel, the queue, was it empty, or did you require it to be at stationarity?
We start with an empty queue. I should have mentioned that, which is why the channel actually it doesn't matter as long as it converges. All we need is that some functions time average of functions of waiting time should converge to expectation over stationary distribution. That's all that's required.
No, the initial ones when the queue is empty, you can get it with higher probability. So you could entangle maybe some delayed ones with the same values as those that you sent earlier, but you don't get much of a benefit. Because,
in the finite block length, I don't know, right? These are asymptotic results, right? In the finite, we have not done finite block length for this. You're right. I mean, there could be the first few will get through correctly, right? So I don't know what that means for finite block length. If you're only allowed to send 100 qubits, I don't know what the best way to send this.
One more question, which is related to your converse, perhaps the specifics of the converse, because that would determine whether this question. Okay, the question is, suppose you actually observe the qubit departing when it departs, for example, and then you can tune your strategy. Tune your strategy in the sense that, of course, you cannot change the time at which it arrives because it's just an arrival. But when the next one comes, you can package it with an appropriate qubit based on past history of departures from the queue. So if that happens, before it goes into the queue, you're able to set an appropriate qubit. That means the coding can depend on past observations. So does the capacity increase?
Coding can depend on. Okay, so we have not considered that situation where the encoder knows, the departure times or what happened to those. I cannot rule out the possibility that if the encoder knows these waiting times, I don't know.
So that's why I asked if your converse somehow makes use of this, and you still are not able to.
Okay, so let me, if I have to see more carefully. So the converse holds, even if the decoder knows all the waiting times of all the qubits, it's still the converse still holds. This is the converse on the screen is the converse. Okay, for additive Q channels. Even if the decoder is endowed with all waiting time sequences of all the qubits it sees, you cannot beat this. Okay, that we have shown. The encoder knowing waiting time, so in this paper, which we put on arXiv, we have made a remark for certain unital channels. I don't exactly remember what we have proven in that. So I don't want to, I can point you to that paper, but you are talking about the encoder knowing the waiting times, right?
That's correct, yes.
Yeah, so we have some remark on that in this paper, which I can point you to. But I don't, for short answer is erasure, I don't think it makes a difference. But for other noises, it does make a difference. Okay, but I have to go look at that a little more carefully. So the answer to your question is decoder knows the waiting time. This holds without modification. Encoder knows waiting times. I think it still holds. I just have to check. Okay.
In the erasure.
Erasure, I don't think it makes any difference. The answer is clearly known. Okay, so you cannot beat this even with W known at the encoder.
So one other question, which I think I should have asked at the beginning itself. So when a qubit is erased, does it completely disappear from the queue, or does it?
It remains as an erased state. Okay.
Okay, so it takes some time to process it.
Yeah. So at the end of everything gets processed. So the difference is that I think Professor Kumar mentioned that customers become disinterested and leave. In that model, I think the load from those disinterested customers just vanishes. Here, the information vanishes, but the state remains. The photon still remains to be processed.
Okay.
Right? The information vanishes, becomes useless. Okay.
Okay. Right. Thanks.
So there's a slight difference. It's not exactly impatient customers. It's bits that vanish, bits that become useless. They exist, but they become useless.
Right.
Krishna, actually, the model I was recalling was the model which you just enunciated. I just spoke it wrongly. Yes, customers would stay in the system, but they would be wasted service. Anyway, the question I have now is that, when we bring queuing networks to bear on communication networks, the entities we are handling there are packets. Here you are handling qubits. Now, is that the way that you'll have quantum communication networks work, where you're actually carrying large amounts of data in qubits? I don't know enough about quantum communication to understand that point.
Yeah, actually, I am also not the right person to answer this. I just talk to people who do this. And my understanding is that presently you just transmit these states. Okay, there is no packetization or header all that is not happening at the quantum level. You find fundamentally you code the information into the polarization state of the electron and you send it. Yeah, I don't know more than. I don't think the abstraction of a packet is well developed in a very quantum sense. That's my understanding.
Okay, thank you.
If there are no more questions, let's end the session. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will be also posted on the webpage. Thank you and have a great evening.
Thank you very much for inviting me. Thank you everyone for attending, and there were some amazing questions. I really enjoyed it. Thank you very much.